So this is a continuation of a video I shot just a few minutes ago where we're solving this problem number 13 for my AP Physics circuit review on WebAssign. And this is from Survey Physics for Scientists and Engineers, Volume 9, Chapter 28, Problem 19, WI. In this problem, we are trying to figure out really the currents going through each of these resistors. This is a power problem, but essentially one way you can do this is to calculate the current through each resistor. And in the previous video I showed how to do this with traditional methods of reducing this down to an equivalent resistance and then using Ohm's law to back out and figure out what the currents and the voltage drops are. Here I want to show you how to do the same problem with Kirchhoff's laws. Now, Kirchhoff's laws and rules are not required for this kind of problem. You only have one battery. We don't have capacitors. We don't have inductors. This is a basic resistor problem. But I just want to show how to solve it with Kirchhoff and to show that it can be solved with Kirchhoff. So in my problem, R1 is 3 ohms, R2 is 2 ohms, and the voltage drop across the battery is 21 volts. And so all of those are plugged in here, and the problem is repeated here. So with Kickoff, what we're going to do is we're going to make some guesses here about which way the current goes, and I'm going to assume that the current is this way, and I'm going to call that I1. And then when we get to a junction here, I'm going to assume that the current then branches off, and I2 will go down like so, and I3 will go down like so, I3. Going to draw on that side there. And so I3 is this way, and this way, joins up with I2, and this current here, of course, is I1 because there's no branching here. So what is I1 this way has to be I1 this way. Okay, so one of the first rules, or one of the rules of Kirchhoff, is the Junction Rule, which says that all the currents coming into a junction have to equal all the currents coming out of the junction. And so we see that if our junction here is B, that I1 is equal to I2 plus I3. And it will be shown that it's better to write it like this. And this is our first equation. So we have three unknowns here. We have I1, I2, and I3. These are the unknowns of the circuit. And we have to then have at least three equations to solve for these three unknowns. So this is our first equation from the Junction Rule. And again, this will make sense here in just a minute why we write it like that. Next is we have the loop rule, which says that the voltage drop across a closed loop has to equal 0. And I'm going to look at this. We have three loops. We have the left loop here, we have the right loop here, and then we have the outside loop here. So let's take a look at the voltage drop across the left side, which is A, B, E, F, A. And the voltage drop across this closed loop has to be equal to 0. So if we start here and look in a clockwise direction, the voltage drop across this resistor, we know is, and I'm going to not use units just to make the math a little bit easier to see, this is 3 ohms times I1, and that's the voltage drop. And so the question is it a positive voltage drop or negative voltage drop? And with Kirchhoff's rules, if you look in the same direction as the current, the voltage drop will be negative, and that is because for the current to run in this direction, this potential on this side has to be bigger than the potential on this side. And so the voltage drop is the final potential over here, which is small, minus the initial potential, the potential before the resistor, which is big, and small minus big is going to be a negative number. We continue on down here, and the voltage drop across this resistor is 2. Again, I'm dropping the units just to make the math easy to see, times I2. And because I'm looking in the same direction as my current is flowing, it's going to also be negative. The voltage drop across this is going to be a negative, because again I'm looking in the same direction as my current, so negative 4 times I1, and the battery voltage drop from here to here is 21, and it's positive because the final voltage drop, this guy here, is my positive, and it's big, and here's my negative. The voltage drop across this is going to be 21 minus 0, which is positive 21. And again, I'm not putting units, but that would be 21 volts, and we know that that has to equal 0. We're going to combine these two here, the two I1s, and I'm going to move all my I's to one side so that they all become positive. So what I end up getting is I end up getting 7I1 plus 2I2 plus 0. There is no I3 term, and that's going to equal 21. And that's going to be my second equation. And it will become apparent in just a few minutes why we write it again like that. We put all the I1s first, and then the I2s, and then the I3s, and then the constant. Then we're going to look at a voltage drop across the right loop, which is B, C, D, E, B, and that voltage drop is 0. So we start here, we come down like so. We're looking in the same direction as our current, so this is going to be a minus 1 ohm times I3. And then when we come up this way, we're going to have the voltage drop is going to be positive this time because I'm looking in the opposite direction as my current. So this is going to be positive 2 ohms times I2. And there's no battery, so that's just going to equal 0. And we're going to rewrite this as 0 I1 plus 2 I2 minus I3 equals 0. And that's going to be our third equation. And I think we can probably stop here, and by hand we can solve this. We probably have enough information here to solve these three equations for our three unknowns. But just for the sake of completeness, and to show you that we can do just continue and get a fourth equation, let's take a look at the voltage drop across the outside loop, which is A, C, D, F, A. And that voltage drop is 0. And so again, I'm going in the same direction as my current, so it's going to be minus 3I1. In the same direction as my current again. I'm just not going to put the 1 there. It's going to be minus I3. Same direction as my current. It's going to be minus 4I1. And then again, my 21 volts plus 21 equals 0. Again, I'm going to group my two I1s and move them all to one side so they become positive. This is going to be 7I1 plus 0 plus I3 equals 21, and this is my fourth equation. So now that I have my four equations, I can use substitution or some kind of system of equations to solve these four equations for our three unknowns. But I'm going to show you how to use a matrix to do that. And the way we're going to do that is we're going to set up an augmented matrix. Okay, so this is going to be our matrix. And over here is where we're going to put the constants, the equality numbers here. And then we're going to line up what the I1 coefficients are, and the I2 coefficients, and the I3 coefficients. So I'm going to start with our first equation, and the I1 coefficient is 1, and this is a negative 1, and this is a negative 1, and my solution is 0. My answer is 0. And then this is going to be a 7, and now you can see why we put it in this order. 2 and 0 and 21, and 0 and 2 and negative 1 and 0. And finally, this is 7 and 0 and 1 and 21. And we're going to double check just to make sure all of our numbers are correct, and they all look good. Okay. And at this point now we can use the TA 84 or 83 or whatever calculator you've got. And what we're going to do is we're going to enter this matrix into the calculator, and it's going to solve it for us. I'll show you how. So first we want to, I'm sorry about the glare, let's see if I can't fix that a little bit. It's a little better. So we're going to do, we're going to use this button right here, the matrix button, which is blue. So for me it's going to be the second command, or the second matrix button. Okay. And then I'm going to come over here to the edit menu by using the right arrow, and I can choose any of these matrices to enter my matrix into, and because A is the first one and it's empty, I'm going to enter the matrix there. Here I have 4 rows and I have 4 columns. Okay, so I'm going to type 4 by 4. This is easy because the 4 by 4, we have 4 equations and we have 4 columns, 3 unknowns, and then our constants here. If we only had 3 equations, then we would use a 3 by 4 matrix, 3 rows and then 4 columns here. Okay, if you had three variables, for example. So the first number here is the number of equations that you have. Okay, so 4 by 4, and then we just move our arrow key into the matrix, and we just are going to enter now the values of each of these matrix positions. So it's a little tedious. 1, 1 is 1, and then -1. Don't forget it's negative, not minus, but -1, -1. I'm just hitting enter after each one, and then 0. And the next row is 7, 2, 0, 21, 7, 2, 0, 21, 0, 2, -1, 0, 0, 2, -1, 0, 7, 0, 1, 21, 7, 0, 1, 21. Okay. And at this point I can quit by doing second quit there. And before I proceed, what I would like to do is do second matrix again. And now I see that A has a 4 by 4 matrix stored in memory. Okay, and I can click on A. That pulls up A to my screen, and if I hit enter, it displays A. And now this is one more chance just to make sure that everything looks right, and it does. Once that's done, the hard part is over. Next we go to second matrix, and now we're going to go over to math. We're going to scroll down to this guy here, which is B in my calculator, RREF, which stands for Reduced Row Echelon Form. So we're going to hit that, and we're going to then tell it what matrix we want to do this matrix manipulations on. So second matrix, I'm going to choose A, close my parentheses, hit enter, and if it's done properly, you'll get a diagonal of 1s. Okay, because we have an extra equation that we didn't need, that last row is going to be all 0s. And what this tells us is these are the coefficients for I1, I2, and I3. I1, I2, and I3. So this says that 1 times I1 plus 0 times I2 plus 0 times I3 is equal to 2.74. And so of course what that means is that I1 is equal to 2.74, and the units are amps. And this tells us that I2 is equal to 0.913 amps. And finally I3 is equal to 1.826 amps. And so all of these currents are positive, which means that in our initial guessing, we guessed that the currents were all flowing in the right direction. if these currents, one of these currents were ever, if we ever calculate a current and it's negative, it simply means that the direction of the current is in the opposite direction of our initial guess. Here it's pretty obvious. The current comes out of the positive side of the battery, flows through, and branches off like so. But if we had guessed the wrong direction, we would have found that the current would be, one of these currents would be negative. The magnitudes would be the same. The negative just indicates that we are guessed the wrong direction. And so if you compare these currents here with using Kirchhoff's solutions with the currents that we found in the previous video, we see that the currents are all the same. So this current here is 2.74, 2.74. This current that is here is 0.913. This is our I2, 0.913, and we found that the current going through the 1 ohm resistor was 1.827, 1.826, close enough for government work. And so the traditional method and Kirchhoff's method gives us the same answer.